Ladies and gentlemen, hey, thank you again for joining me on today's webinar, which is simply the 10 reasons to do FMEAs. Now, I appreciate there's going to be a wide range of FMEA experiences out there, some good, some bad, somewhere in between. So, not only am I going to talk about 10 reasons to do FMEAs today, I'm actually going to really narrow the focus, and that is 10 reasons to do amazing FMEAs. FMEAs that are done poorly are rubbish activities. They are activities which focus on creating some sort of template or spreadsheet or something that is there to satisfy some compliance requirements somewhere in a contract or just a boss's gut feeling, whatever reason. I've seen plenty of bad FMEAs done in my time, but the FMEAs that are done really well always, and I mean always, have good results. And the reason is because amazing FMEAs focus on problems that matter, and we're going to go into that today. So today is all about 10 reasons to do amazing FMEAs, not just any FMEA, an amazing FMEA. So for those of you who don't know what a FMEA is, we're going to go straight into a very textbooky definition of a FMEA. And there's sort of no way to get around this jumble of words. A FMEA is a method designed to identify and fully understand potential failure modes, their causes and their effects on the system or end users for a given product or process, assess the risk associated with these potential failures, prioritize issues for corrective actions, and finally implement these prioritized corrective actions. Now that is a mouthful. We really do need to have that definition here because technically that's what it is. But a bad FMEA could technically satisfy this definition. A great FMEA could technically satisfy this definition. An amazing FMEA certainly satisfies this textbook definition. So not only am I going to go through 10 reasons why you should want to do an amazing FMEA, in the course of doing that, hopefully I'll communicate to you guys today what an amazing FMEA looks like. So one of the challenges we have as reliability engineers is trying to motivate people to get excited about FMEAs, and definitions like this don't help. And we use, some people use the ideas of, things like brand value or reputation or things like that. These are reasons we want to do reliability and take reliability seriously. We want to avoid failures in the hands of customers because that is obviously going to hurt the bottom line later on. But that is great as a company or organizational goal, launching missions, low warranty, reputation, brand value, all those sorts of things. But those lofty goals are very difficult to percolate down to the coalface. How do you tell a hydraulic engineer that what they do needs to make sure that they won't impact reputation in a negative way 5 years from now when the full system they're working as part of is going to be released to the customer? It's a very abstract goal, and abstract goals quickly get replaced with specific goals at the coalface. Do this on time, do this on budget, make sure it's no bigger than this, make sure it doesn't weigh any more than this, make sure it doesn't cost any more than this. Those are the sorts of very specific goals that filter down the coalface and quickly replace abstract high-level goals which sound nice, like reputation, brand value, things like that, but in practice don't motivate people who are designing your product, system, or service. So just bear that in mind. Why do we want to do FMEAs? Reason number one is if you do FMEAs, do an amazing FMEA, I should say, you have no bad experiences. Now I need to qualify this astounding claim because everyone has bad experiences when they're creating something from scratch. But the thing that FMEAs really focus on driving down are those bad experiences that you experience during production. Now, have you had a bad experience? I'm sure you've had. For example, when you are trying to do reliability stuff, Have you ever been forced into a FMEA which has poor facilitation, or you worked really hard on doing a reliability report or doing some sort of testing, and it didn't change anything? Did you just sit in a room of people who are forced with cattle prods to do some reliability engineering activity on that particular day? Or are you just doing it to satisfy contractual requirements, or your boss just wants it done, or you're doing it because some standard has been imposed upon you and therefore you have to say that you've done this level of effort? Now, an amazing FMEA makes sure that people who turn up to that FMEA have no bad experiences. One of the reasons why is they're bought into it and they walk away from the FMEA, which they are trained for and prepared for in advance, with a raft of really good pointers on how things can improve in their small domain. Now, one of the reasons we often have bad experiences when it comes to FMEAs, I should say, is because of this guy here. I often use the so-called enemies of reliability. And first and foremost is our infant manager, that boss who is always pressuring you to do things on time, on budget, and he or she often wants what we call WTF, which we all know stands for the wrong thing fast. And the wrong thing fast is a painful experience. That's where you get forced into a room, you get forced to do something. You're told, I don't care what the outcome is, or there is a passing fancy at the outcome, but in practice, you're being told to do this because for whatever reason, organizationally, your organization says this needs to happen. And when we have our infant manager driving the culture of FMEAs or any reliability activity, where they demand the wrong thing fast, it is a painful experience. That is a bad FMEA, leads to bad FMEAs. The other bad experience that we often get is when we have this process seller, the person who wants you to do something just to satisfy a checklist that he or she has come up with or has been told to impose. For some reason, these people exist and get this perverse satisfaction out of making you do stuff to satisfy their checklist. They really enjoy ticking boxes. Now, this person really doesn't care how you do it. They just want the report ASAP. That's not an amazing FMEA. That is a painful experience where effort is confused with outcomes. So these are our two enemies of the amazing FMEA. Now, the friend of our amazing FMEA is the amazing FMEA facilitator. Now, if you go back to our definition of what a FMEA is at the start of this webinar, it was a very wordy textbook thing where it says you need to do this, go through failure modes, root causes, correct them. But the heart of an amazing FMEA is, the symptom of an amazing FMEA, the symptom's the wrong term. What you need to have to result in an amazing FMEA is an amazing FMEA facilitator, someone who is passionate about what they do, knows what they're doing, prepares the participants, makes sure that training is up to speed, everyone walks into that room ready to go, and everyone walks away with an amazing experience. Now, an amazing FMEA, usually we have a rule. We have around about 4 to 8 people. And what we want to do when we have that group of 4 to 8 people is have that amazing facilitator extract all that useful information out of those participants who are cross-functional representatives, not the junior guy who drew the short straw, not just the entire electrical engineering team, because they're the only ones who take it seriously. The mechanical engineering team didn't turn up, so let's just fill all their vacant spaces with more electrical engineers. No, cross-functional representatives. You can see in this picture here, which sort of gives you the idea of a typical FMEA classroom layout or FMEA room layout. You have no laptops apart from one person who's the scribe. And that scribe is recording everything we do every single step of the way. So this is what a typical amazing FMEA room looks like. You have the projector screen where everyone can see what that scribe is writing. And of course, a facilitator who typically is not part of the FMEA itself, in that they don't have a really good, they don't have some skin in the game. They're often externally provided. They're often external contractors or consultants who do this for a living. They're the ones who facilitate these experts who are responsible for creating something, responsible for finding the process, responsible for making something amazing. They facilitate the discussion, and that's perhaps the most important part of what a FMEA is. So a FMEA is all about preventing problems, making our first design a reliable design, and we'll get to that very, very shortly. So that's the first reason you want to do an amazing FMEA, no bad experiences. The second reason you want to do an amazing FMEA is no complicated equations. One of the many criticisms reliability engineers get is that, oh, all this statistics and Y-ball this and exponential that, oh my goodness, it's just too complicated. Well, lucky for you, or lucky for people who are complaining to you about reliability being too complicated, FMEAs involve no complicated equations. Now, most reliability engineering courses go something like this. They start with a horrific outcome of something failing. There's a nuclear power plant exploding or melting down. In this case, it's an airplane crashing, train derailing. It could be any number of horrific disasters that have been indelibly inked on our collective psyche over the years. Tacoma Narrows Bridge is a very famous one as well. And so we start with this imagery of just catastrophe and disasters. And then in that reliability engineering course, the instructor, who sometimes is what we call a ponderous professor, says, hey, remember that airplane that crashed, or that nuclear power plant that melted down? That's why reliability is really, 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 really important. Now let's go into all sorts of equations and charts and stuff. Now, the FMEAs are the opposite of this, and our ponderous professors, those guys and girls who somehow try and enshrine complex statistics and mathematics and reliability engineering, tend to not like FMEAs. The reason being is that from their perspective, FMEAs involve subjective assessment and not years of painstaking data analysis, which this person loves. So if you want to avoid complicated equations, or you work in a team where there is a common refrain that reliability engineering is too complicated, well, FMEAs are the tool for you, I should say, because they involve no complicated equations. And the reason why is because measuring or analyzing reliability can be important, but it's not nearly as important as designing in reliability. And FMEAs are all about making your first design a reliable design, so that you don't have to fix stuff or redo stuff that you thought you did well. Which brings me to the next reason, number 3. Why do you want to do amazing FMEAs? Because there are no complex, expensive fixes to your design, your process, if you do an amazing FMEA early. Let me explain, because that might sound like an outrageous claim. So in many of my courses, I use this example, this system here as an example, a smart lock. A smart lock's an amazing system. It has lots of different technologies represented in it. It represents, I suppose, emerging technological trends where smart technology is becoming more and more prevalent in everyday objects and things like doors. And so this is a fantastic example system for me to demonstrate how useful FMEAs are. So if we look at this smart lock in greater detail, there's obviously a ton of different components and subsystems and assemblies that all need to come together to make our smart lock work. Now, a smart lock is essentially a mechanical lock, a traditional mechanical lock with what we call smart technology. It's got its own electronics. It hooks up, it can communicate with your phone via Bluetooth. It can communicate with anything through the internet. And so you can do all sorts of things like have that lock automatically unlock when you, with your smartphone in your pocket, walk up to it. And there's tons of other things that smart locks can do as well. You can lock or unlock your smartphone from the other side of the world. Sorry, you can lock or unlock your smart lock from the other side of the world if you have a smartphone. So how is this relevant for FMEAs? Well, let's just say that this electric motor, which is connected to the circuit board, like as you can see here with these two wires, let's just say these connections, these soldered connections, perhaps they're prone to failing when our smart lock is in a door which is slammed hard a lot. Now, think of any one of us who have had children ranging from 3 years of age all the way up until 25 years of age in some cases. It just takes a temper tantrum for our poor front door with a smart lock attached to be subjected to a very emotional slam. And now that could wreak havoc on our smart lock because we perhaps didn't anticipate the level of stresses that a slamming door would exert on the solder joints that connect our electric motor to the circuit board. And solder joints aren't the strongest thing in the world. So just think about how such a simple failure mode could completely immobilize your smart lock. And even though it's got tons of amazing technology, one of the simplest ways your thing can fail perhaps might be the most dominant way or the most pressing reason that customers aren't happy with it. So what can we do? Well, there's tons of things we can do. Before we design it, we can do things like put these, what we call corrective actions in play. Instead of having a thin gauge wire, we have a thicker gauge wire to provide more contact area with the electric motor terminals. We could also make sure we have shorter wires to limit the total mass that our wires have. So when the door does slam, there's less momentum being transferred to the contacts or to the terminals. Another thing we can do is have clips to physically restrain that wire or cable. When it comes up to the circuit board, instead of having solder joints, we can have a socket and plug instead, which makes it, by the way, a lot easier to assemble as well, which is a really useful thing to do. We could also understand that even though we're going to have solder joints, we can't get away from solder joints at the electric motor end of that cable, we could incorporate visual inspection of motor solder joints when we get them from the supplier. And we could also have surveillance automated testing where we say take 1 out of every 10 motors from the supplier, subject them to more stringent examination to make sure those solder joints are good. Now, these are some really simple and great ideas to make our first design a reliable design. And this is how reliability happens. When you're able to think of things early enough, when you're able to get ahead of the curve, when you're making your first design a reliable design, you have the ability to incorporate all these really simple ideas really inexpensively because you haven't designed your thing yet. So this is what FMEAs are all about. Those no complicated, expensive fixes, which only become complicated and expensive because you realize something is wrong after you've designed the rest of the system. Which leads on to the next reason you need to do a FMEA, or you should do a FMEA, I should say. There's no, I wish we could have, there's no, I wish we thought it would have, I'm struggling. There is no, I wish we would have thought of that before we insert some time in the past here. That is, we don't regret to ourselves not doing something 2 weeks ago, 2 years ago, 3 months ago, because we took the time to think about what might have gone wrong before we rushed into designing our system. And so I'm sure every one of us, whether it be a home renovation project, through to homework, through to any endeavor that technically minded people throw themselves into, there have been times where we go, oh man, if only I had thought of that before I went and plastered up my entire wall, I would not have to pull the entire wall off and start again. So we want to avoid being frustrated. It helps us avoid becoming this frustrated engineer here. FMEAs make us stop and think before we jump. Engineers tend to be tigers. Tigers are the opposite of turtles. Tigers are what we call people who want to race in and solve problems. Turtles are people who want to go on their shelves and wait till the problem goes away or someone else solves a problem. Not us. We're engineers. We're technically minded people. We want to jump and solve problems, and that sometimes gets us into trouble. But if we use FMEAs, it forces us to stop, think about where we are about to jump to, what problem we're trying to solve, and make sure we're solving the problem without incorporating tons of others later on. Which leads us into the thing I've been saying multiple times, that our first design is a reliable design. And that is huge. A lot of organizations want to rush to make something that can work versus something that will work. So instead of having a beautiful, slick looking smart lock prototype, how many of us have been involved in organizations where the first working prototype of whatever it is they're making looks more like the one on the right? It's bolted together with temporary fasteners. There's stuff leaking out because we had to glue something together because it didn't fit perfectly. The handle doesn't fit, so we have jerry-rigged some sort of wrench or spanner to make sure we can test the shaft being turned. There are so many prototypes, first prototypes, which look like the one on the right. But if we slow down, do a FMEA, understand our system, understand what's going to likely go wrong, our first prototype is going to be so much closer to the final prototype that things like budget and time to market and schedule become a breeze. And remember, we're not talking about rocket science here. If you and your team are smart enough to design a smart lock or whatever it is you're designing, then you're also, by definition, smart enough to know what will likely go wrong. And for me, it's all about harnessing that corporate information in a really usable way to, again, make sure that our first design is a reliable design. And when we do that, we save lots of time and money. Now, I'm going to go through an example I often use in my courses and in my webinars about how we can compare what we call traditional design processes with design processes that use the reliability mindset. Now, the traditional approach to designing something is essentially build, test, fix. We have an initial raw design effort, which is represented by this red hump here on these axes. On the horizontal axis, you can see the horizontal axis represents design time or schedule, the duration we spend in this particular phase. And the vertical axis represents the amount of money we're spending along the way. So this little red hump here represents our initial design effort. And once we have finished our initial design, then we need all sorts of engineering support to turn our first design into a manufacturable design or a usable design. We obviously need to certify or somehow validate or verify what we do. And of course, along the journey, when we test our prototypes, we then have to eliminate failure modes and mechanisms. Now, the reality is that big monstrous hump of time and effort is us remedying preventable problems. Now, conversely, if we use the same approach where we use a reliability mindset, we invest a lot more time and money up front in our initial design, but have a look at what happens to the follow-on activities. Because our first design is a reliable design, we don't need to spend nearly as much time eliminating failure modes. We don't need to spend nearly as much time having other engineering support functions turn whatever it is we created, whatever Frankenstein thing we created, into something we can manufacture. And of course, certification becomes a problem because that first design is a reliable design. So if we compare the overall time and cost profile of our process that involves a reliability mindset with our traditional approach to designing stuff, it turns out that in this example, using that reliability mindset, slowing down, investing more time and money into our first design meant that overall, our product was 73% less expensive to produce, and we got there in half the time. So when people say ask you to choose between reliability, time, and cost. You get to have two of those, not all three. That's nonsense. If you invest in reliability from the start, you really drive down your schedule. You really drive down your budgets. And the reason is because we're preventing problems. This is what FMEAs are all about. Now, for those of you who haven't seen this before and are really questioning where this comes from, I'm going to tell you that I'm going to explain how this is a real case scenario. Before we do that, I want to go back to our enemy of reliability, our infant manager, that person who has that money bomb right next to their head, who wants the wrong thing fast. The reliability mindset makes this guy or girl go crazy because we ask them to slow down, invest more time and money up front into getting our first design reliable, and that just doesn't gel with how they're built. They want to demonstrate progress as quickly as possible for as little money as possible. That's how they get their kicks in life. So the infant manager almost certainly will destroy any decent reliability engineering activity or effort, and that includes our amazing FMEAs. Now, all these curves, all these lines, all these humps, these weren't things that I made up or lines that I randomly drew. These were lines, this is based on data from an actual study. So they compared how they went about designing liquid fuel rocket engines with a build, test, fix, or traditional mindset versus the approach with the reliability mindset, making the first design a reliable design. So we don't have many really well-researched studies like this because organizations that take reliability seriously don't have the bad example to compare to. But so these sort of studies are very rare, but very precious. And it just goes to show how important making our first design reliable, how important it is to make our first design reliable. Number 7, reason number 7 you want to do for me is making your thing better than your competitors. Now, this might sound a little bit weird or a little bit different to some of you out there. Reliability engineering is often associated with making the idea of some design team come to life in a way that, that minimizes the probability of failure. Again, that is a misconception. Reliability engineering, yes, it's all about failure or preventing failure or minimizing the chance of failure. But what does failure mean to you? Well, sometimes if we simply define failure as any event where we fail to meet our customer or user's expectations, then FMEAs become an incredibly powerful tool. So let's look at that with an example. Here is a Motorola two-way radio. It's a very simple radio used across the world by law enforcement agencies, work crews, militaries, so on and so forth. And the idea is that this radio, it has what we call a push-to-talk button on the side, which means that every time you want to talk to the network you're on, you push the button, say what you want to say into the speaker, which now turns into the microphone. Everyone else gets to hear it, release the button, and then you can hear what anybody says in response. It's a very simple radio, obviously some complex electronics on the inside, but it's an amazingly powerful bit of kit. And Motorola make fantastic two-way radios. They are the industry leader, some might argue, and because their two-way radios are really great to use. Now let's look at how they keep ahead of the game. All their competitors are catching up, or always seem to be catching up to what Motorola has in their next generation of two-way radios. And we're not talking about amazing space science, we're just talking about good design. So for example, these two-way radios are used by military operators, and the militaries across the world are a huge customer base or market segment for Motorola's two-way radio division, directorate, whatever it is they call themselves. Now, I'm ex-military, and I dare say a few of you are ex-military as well. when you're out doing your thing, you are covered from head to toe in uniforms, protective plates, all sorts of different things. And that includes often big, thick, heavy gloves. It can be cold out there. And even if it's not cold, when you're crawling along the ground, you need to use your hands to go from point A to point B. So you need to have these really thick, heavy gloves to make sure you don't have bits of glass or sharp rocks force their way into your soft, sweaty palms. But you also need to use a two-way radio from time to time to let people know what's going on. So two-way radios have had historical problems with military operators pushing the push-to-talk button. Now, in any other scenario, any engineer, any technically minded zealot could argue that, hey, if you can push that button and it conforms with my specifications, my thing hasn't failed. I don't want to hear about you saying, well, it failed because it's very hard to use with these thick gloves. It's sometimes too easy to push. Sometimes it's hard to locate. No. If you get caught up in the whole, I'm the engineer, I'm the technical expert, if you can push a button and it works, then you are going to rapidly design something that no one else likes. Not Motorola. They knew what they needed to do and they used the FMEA to get there. So, like I said, they defined failure to be an event where the push-to-talk feature is difficult to press in military gloves. And they completed a FMEA based on this, what we call failure mode. Not just the thing breaking or catching fire or just not working anymore. They defined failure as something difficult. So an event where it was difficult to use by a customer. And so they came up with these corrective actions. The first corrective action was they improved the textile area on the push-to-talk button. And the reason they did that is because it makes it easier for the operator with thick military gloves to rub their thumb up and down the side of the two-way radio and know when their thumb is on top of the push-to-talk button. The second corrective action they came up with was to incorporate a colored ring around the push-to-talk button. The rest of the radio tends to be dark color or black. So they had, in many cases, a bright blue ring around the push-to-talk button, not big enough for it to give the soldier away in the battle space, but certainly something that the soldier could see up close if they needed to rapidly identify where that push-to-talk button was. The third corrective action they came up with was these tactile locator ramps, which is a fancy word for essentially saying that they had these bumps at each end of the push-to-talk button. So even in pitch black of night, you could rub your thumb up and down the side of your two-way radio, or just get used to holding the two-way radio such that your thumb naturally lies between these two tactile locator ramps, and without you having to look down, or without you being able to, with you and your thick gloves in the middle of the night, you would be able to easily feel where that push-to-talk button is. And they also looked at how hard you had to press that button and how far it needed to go. So in this case, they increased the activation force and the travel, which meant that you needed to exert more force with your thumb, not an uncomfortable amount, not an amount that would otherwise make it unpalatable for other users, but in a way to make sure those big, buffy military operator hands and those big, buffy military operator gloves wouldn't inadvertently push or activate the push-to-talk button without them having that tactile sensory feedback that a naked thumb gives you. So these are 4 corrective actions that Motorola was able to include in essentially the first design of the next generation of their push-to-talk, two-way radios. And you should be able to see that these characteristics are really, really simple. There's no earth-shattering technologies involved. There's no exorbitant costs either. Sure, you need to change the molding for the case, to have these tactile locator ramps, for example, but everything they did was essentially cost them essentially next to nothing in terms of incorporating into the next design. But this is the sort of stuff that speaks to users and customers. It's not the fancy stuff. If the basic stuff doesn't work, the basic stuff doesn't feel comfortable, then you get a bad rep. When you think about buying a bicycle, you might walk into a bicycle shop, you might have it down to 2 bicycles which have roughly the same price, have roughly the same specs, weigh the same. What are you going to do to choose which one you're going to purchase? You're going to test ride each one of those 2 bicycles. The one which has the most comfortable seat will be the one you buy, without a shadow of a doubt. So the comfortable seat, the comfort of the seat is often way more important than the Shimano gears or the hydraulic brakes or whatever it is that makes that bicycle amazing. If that bicycle seat is not comfortable, good luck trying to sell it. It's these really simple things that FMEAs are wonderful at helping us identify to make sure that not only our first design is a reliable design, but our first design is an amazing design, period. And when you do that, when you go through this process, you understand what your thing can do. And when you understand what your thing can do, that means that hope is out of the picture. What I mean by that, there have been plenty of times and plenty of organizations I've been involved with where people are designing stuff. They go through the process of having the hydraulic pump here, steering over here, waveform converter over here, get something which can functionally, at least on paper, work when it's all put together, and just hope the customer likes it. Hope is really a bad strategy to have when you are designing something new and amazing, especially if you're trying to get ahead of the curve. Now, the military defense industry is great for relying on hope. That is, we have contracts that go out to defense contractors, say, please design vehicle, weapon platform, whatever it is with these essential requirements. And we just hope when it comes back, it's going to be put together or designed in a usable way, in a way that makes sense for our soldiers, sailors and airmen. But 9 times out of 10, when we rely on hope, hope disappoints us, because hope is not a strategy. Hope is a feeling, it's an emotion. Now, if you do a FMEA and if you're involved in a contractual relationship and you're heavily involved in FMEAs, you can influence how that system comes together in a way that eliminates hope. If you understand what your thing can do, you understand how you're going to disappoint your users or customers, which means that you have all those really simple, inexpensive design characteristics built into your first design to make it both reliable and available. So that's number 8. The 9th reason you should be excited about FMEAs is that they tick other boxes. I did rail against ticking boxes in this webinar, so let me explain. FMEAs are a genuine risk management framework. We obviously have to deal with risk in everything we do. And sometimes we look at risk management as a separate activity, something which overarches what we do. We design, we manufacture, we maintain. And at the end of each month, we have a risk management meeting and work out what this idea of risk is, what we can do to drive down risk to something as low as reasonably practical, so on and so forth. It almost feels like we stop doing our day job to think about risk. But if you embed FMEAs into your design process or your manufacturing process, so that you're coming up with these wonderful ideas like tactile locator ramps on your two-way radios, and wonderful ideas like securing the wire within your smart lock, then risk management is actually part of what you do without you even knowing it. Oh, and by the way, if someone wants to audit your risk management framework, if you've done it for FMEA properly, your worksheet is sitting there ready to go, explaining all the risks you've identified and what you're going to do to address them. This is a big deal in places, in organizations or scenarios where safety is crucial. Obviously, safety is always crucial, but not all products, systems, or services have a safety-related risk associated with them. But if you do have safety, if you do need to take into consideration safety, then having a FMEA, which is organic to your design or manufacturing process, essentially means that people are doing risk as part of their day job. But there's lots of other things that FMEAs can help us out with as well. They can help us generate design verification plans and maintenance regimes, system and component test plans, process control plans, manufacturing specifications and tolerances, to name a few. The number of times I've been asked, hey, by this customer or organization over here, hey, we're manufacturing this device. Can you please give us a standard that will tell us what tests we need to create to make sure our thing's reliable? That is dumb. If you do a FMEA, you automatically know what your most dominant failure modes are, which means that part of your corrective actions, once you've secured that wire, once you've included those tactile locator ramps, if it's to do with, for example, fatigue, one of your corrective actions could be to incorporate a very specific fatigue test in your design verification plan to make sure the alloy that your supplier used to manufacture the handle doesn't have impurities or surface blemishes that would lead to a fatigue failure. And that's where your testing relates to things like reliability in a way that avoids you relying on hope as a strategy. So FMEAs tick so many other boxes as well, if they're done well. And the last, and perhaps, I won't say most important reason, but it's a very crucial reason for people who are focusing on their own emotions and their own feelings when they're creating something and need to make it reliable, is that FMEAs are good at eliminating overwhelm. What do I mean by that? Well, here is a very basic representation of the production life cycle of something. And the thing we do at every step of the way is make a decision. And so decisions are everywhere. Decision, 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 decision. And sometimes the magnitude of a particular decision or the number of decisions can paralyze us. That's called overwhelm. So let's have a look at this in a slightly different way. This production life cycle is essentially a series of decisions. And as our good friend Fred always says, reliability happens at the point of decisions. Oh, and deciding to not do something or avoiding making a decision is also a decision. So you can't get out of it by not turning up to that decision-making process. So reliability happens at every one of these decisions, and that can be overwhelming. Well, if we look at if we look at what this means for reliability engineering, and you go to a textbook, you will see an overwhelming amount of possible activities that you could undertake when you design your thing. Well, what do? Do you use all of them? The answer is no. You should only be using a couple of these, the vital few, we say. But which ones are the vital few? Well, if you're in any doubt, start with a FMEA. Now, a system FMEA is great because it focuses at the system level. It's a high-level analysis. This is one of the FMEAs you do up front, where you prioritize the vital few. And it informs what we call a design FMEA, which we'll look at very shortly, where the design FMEA examines components and subsystems in a much more detailed way. And system FMEAs take into consideration safety. They take into consideration single point failures. And most important, perhaps, interfaces, how our components interact with each other. If you don't consider interfaces, you can almost guarantee that your thing will fail because of an interface problem. We know as a rule that about 50% of failures we see in the field occur at interfaces. Look at the number of spacecraft that have imploded on the surface of Mars at a great rate of knots because one software component was thinking in terms of foot-pounds and the other software component was thinking in terms of Newton meters. Something as silly as that has doomed billions of dollars of space effort or space flight effort because no one considered the interfaces. System FMEAs are great at that. It also allows us to look high level at service support and maintenance and all those things that are required to make sure our system works throughout the journey. And of course, user experience, how our user is going to interact with our thing, how the thumb is going to somehow find its way to the push to talk button. That happens at the system FMEA level. And beyond that, system FMEAs help us identify functional relationships that are unique to our system. And perhaps finally, they really drive home really study how humans interact with our thing. So system FMEAs are great at understanding what your system is, what those vital few are, looking at those interfaces, and otherwise getting the ball rolling for your reliability engineering effort. The next sort of FMEA we're talking about here is that design FMEA. Now, we do design FMEAs on individual components and subsystems and assemblies. Now, we don't do design FMEAs on every component. The system FMEA will tell us which ones we need to focus on. We don't. If everything's important, then nothing's important. But design FMEAs are all about improving the design, coming up with those reliability activities that are going to eliminate specific failure mechanisms. And that's how we avoid the overload. Do we need to do a specific test? Well, a design FMEA is going to tell us. Do we need to use this sort of material over that one? Well, a design FMEA is going to tell us. And if a design FMEA can't, the corrective action should be we're going to examine this further. We're going to conduct this test to work out if that alloy is going to work in this application, which is where those test plans I was telling you about comes from. And the other thing that design FMEAs help us out with are those manufacturing specifications. How thick, what's the diameter of my shaft? How thick can it be? How thin can it be? Design FMEAs tell us how thick or thin our shafts need to be, which then drives things like system reliability analysis, because we know what's going to fail if it is going to fail, which once we analyze helps us make a safe and reliable operation. Now, because we've done a system FMEA, we know how a component's going to interact with other components. So a design FMEA is going to make sure that our thing is designed in a way so that it will interact with the things that are next to it and the things that it exchanges information or energy with. So that's where design FMEAs are really, really useful in making sure that those interface problems don't become problems. So reliability, life modeling, all things like physics of flow and accelerated life testing, we talk about these a lot. Do we need to do them? Do a design FMEA and you will find out. So design FMEAs do all these wonderful things. System FMEA at the high level says, hey, we need to do design FMEAs on these 30% of all our components or subsystems. And when we do that, we get some amazing corrective actions, which help us make sure our first design is an amazing and reliable design. Now, obviously not everything is mechanical. So sometimes our design FMEAs become what we call software FMEAs, where we focus on improving the code. And we design things like fault tolerant software. We know what will happen if our thing fails, because our system FMEA has already gone through that process. It says, hey, if this software code doesn't work, then our rocket implodes and people die, or whatever the effect is. So we're able to prioritize our effort to make sure our software can tolerate faults, which results in what we call high quality code, which is, for example, easy to fault find and debug. The amount of software code out there that is written by one guy on a 72-hour straight period of being awake, such that, and it works in the first couple of tests, but 3 weeks later, gremlins emerged. And not even that guy who was able to who wrote that code in that 72 hours, fueled with Red Bulls and Monster energy drinks, not even he can go back and work out what he was writing at that point in time. So it takes a humongous effort to pull what he did apart to work out what needs to change. So even just having good quality code can help us in terms of a reliability moving forward. So that's a software FMEA. It's sort of analogous to design FMEA, but at least for software. So let's go back to design FMEAs, where one of the outputs is manufacturing specifications. Why am I going to focusing on that one? Because another sort of FMEA is a FMEA which focuses on manufacture, a process FMEA, where we look at how we set up our manufacturing plant to make sure whatever it is we're making aligns with those manufacturing specifications a design FMEA came up with. So our process FMEA, it's all about manufacturing process improvement, process control plans, how we come up with plans to make sure that all our robotic arms, all our milling machines are doing what they need to do. What are we looking for to make sure that our parts that come off the conveyor belt are good to go? Which sounds very abstract, but those of you involved in manufacturing, you know that the sooner you get on top of your process, the sooner you get to high volume manufacturing, which is what you need to do to reduce time to market. And this results in high quality parts, which aren't the cause of failure in the hands of your customer later on, and ensuring that your product is built to design requirements. It is safe to use with nominal downtime and minimal rework. What are we talking about there? Scrap. We don't want to have to for example, simply test everything that comes off the conveyor belt and throw away 40% of our ball bearings which weren't manufactured within specifications. That's a terrible amount of scrap. That's a terrible amount of waste. We want to focus on a process in our manufacturing plant which involves very few defects. That's what process FMEAs are all about. Manufacturing, assembling, shipping, all those different things are included in our process FMEA. So those are the big ones: system design, process FMEAs. They are the ones which those are the big three that help make sure that we avoid that feeling of overwhelm, that tell us what we need to do. And in the notes, you've got a couple of other references to other FMEAs as well. So if you do want to learn more about some of the other FMEAs that are out there, look at them in the notes and feel free to reach out to me outside of this webinar to talk about them further. Now, the end state of a good FMEA strategy is a simple approach to making reliability happen. Because if your approach is not simple, it's not going to happen. Now, FMEAs introduce a real feeling of simplicity. Sure, you might need to do training. Sure, you might need to work on creating a FMEA culture in your organization. But when you focus on investing in that culture, then what you get is a simple process or a simple set of things you need to do to make sure that your first design is a reliable design. Now, one thing I always say at the end of these sorts of conversations is that if reliability engineering isn't making you money, then you are doing it wrong. So FMEAs should generate huge returns on investment. If you remember that liquid fuel rocket engine example, look at how much time and money was saved overall by investing a smaller amount of time and money up front. And it all comes down to stopping and thinking. And that can be hard to do for us reliability engineers. But when we do, and we use tools like FMEAs to get there, we make our first design a reliable design, which means we get off that build, test, fix treadmill. We only focus on the vital few things we need to. There's no overwhelm. Safety just happens because it's part of what we do. We manage risk without even knowing it, but it's all done. That's what we want to achieve when it comes to making sure our first design is a reliable design. But not only that, we can make our first design an amazing and reliable design as well. If we don't focus on preventing problems, then the only hope we have for making reliability happen is my good friend, the reliability fairy. Now, the reliability fairy is a mythical creature that is able to somehow sprinkle reliability on the thing you're creating once you've finished the design and manufacture. That in practice doesn't happen, because once you find a problem during your final production run or at the end of your design life cycle, it means you have to go back and redo stuff you thought you had already done. And the later you find out about it, the more rework you have to do. And that amount of rework is typically not included in budgets. That's where our overruns come from. That's where our schedule delays come from. And the only way you can get around that, or two ways you can get around that: one, preventing problems by using a FMEA or a similar tool, or two, hoping that the reliability fairy is actually a real thing, and it's not. So we need to focus on preventing problems from day one. And when we do, we have those production processes which tend to have few fires, few catastrophes, few crises, few budget overruns. Schedules are usually exceed our expectations, and everyone is happy. And the reason we can do all this stuff with FMEAs is because we have these things called nuggets of gold. A nugget of gold is what at least I refer to as that little bit of corporate knowledge that you might know about the thing you work on. So here are some examples here. We're certainly not going to go through all of them, but these are examples of nuggets of gold that you and your team have spread amongst you. So for example, we know that as a rule, any material change, including a corner, hole, or weld, will amplify stress. That little nugget of gold is absolutely fantastic because during our FMEA, we can actively ensure that before we design anything, we specify minimum radii for our corners to make sure that we don't amplify stress to an unacceptable level. And all of a sudden, we can have all those little simple design changes or design characteristics involved from the start. And that means we have that really robust, reliable design because we harness all these nuggets of gold that you, me, everybody else around us have. The key is bringing them together with that amazing FMEA facilitator to extract them out, prioritize them, and make them part of what you do. So for metals and alloys, we have all these little nuggets of gold. Again, these are in your notes. And the reason I'm having these shown relatively quickly is because the main point is everyone has lots of these nuggets of gold. Plastics and rubber. These are some typical things we consider for plastics and rubber. Ceramics. Do we want to have, for example, strength or surface hardness? That's a big deal. Are you designing something which is going to be structurally sound, or is the ceramic going to be part of a bullet-resistant vest? Composites and adhesives, very, very strong. Very easy to degrade if you use them in the wrong environment. Electronics is a big one. Look at this one over here. We know as a rule that if you derate your components by around about 50%, you can often decrease your failure probability by around 30%. And that's a huge improvement in reliability. And it might involve an insignificant change in your budget for your electronic components because a 10 picofarad resistor rated to 20 volts is marginally more expensive than a 10 picofarad capacitor rated to 10 volts, for example. And there's many, many more nuggets of gold out there. And all FMEAs do is get them into, is collect them, organize them in a very empowering, useful, non-intimidating way with an amazing FMEA facilitator so that everyone's experience is evident in that first design. And this is great because that means that everything you need to do to, you already have what you need to do in order to make, you already have what you need to do amazing FMEAs. I'll get that out eventually. So it shouldn't be an intimidating process. You do need to spend time investing in that amazing FMEA facilitator, training your team, coming up with your own FMEA approaches. But once you do, everything becomes orders of magnitude simpler thereafter. And it all comes back to the idea that everything fails through a vital few ways. So FMEAs focus on these vital few. We don't want to fix everything. That's called over-engineering. We want to understand what the vital few things are, make sure they are designed out of our first design, and lo and behold, you have a very smooth production process. So those 10 reasons you should do, and you want to do FMEAs, I should say. 1, no bad experiences. Amazing FMEAs are empowering, dare I say it, in some cases fun. Sure, you can be tired at the end of the day, but if you walk out of the FMEA with all sorts of great ideas for how you can make sure that your electric motor is not going to embarrassingly fail in your system later on, then that's a really good thing. It's a really good feeling. There's no complicated equations. If you do it right, your fixes are inexpensive because they're done early. They're almost insignificant parts of the design. It could be simply moving a a very hot power supply from one side of your case to another to make sure it doesn't impact another component which is sensitive to temperature. How simple is that? It's essentially free, just having your power supply isolated from thermally sensitive bits of kit, and it's fantastic. It's free stuff if you think about it in time. Which means that we don't wish we could have done something way back when we thought of it, because we have actually gone through the process of thinking about it. Which means our first design is a reliable design. We save lots of time and money. And if you recall the Motorola example, our thing is just better. It's better without us having to invest a ton of time and money into making it better. And when we do that, we understand what our thing can do, so we don't have to rely on hope, which is not a strategy. We tick all sorts of other boxes. Risk is part of what we do. We live and breathe risk without knowing it. We come up with test plans without us having to nervously look for or scramble for a standard later on. And when we go through this process, we invest in it up front, we do not get overwhelmed. So, are there any questions? I'm more than happy to stay around for as long as possible. I see a question from Hesham. Yes, the presentation, a PDF version of this presentation will be on the Ascendo website where this webinar can be found. So we won't send it to you, but if you come and check out this webinar on the website thereafter, once it's been uploaded by Fred, you will have a PDF version of these slides. Are there any more questions or comments? Thank you, Brian. So just maybe one thing that Brian has, for whatever reason, reminded me about, when you're in an organization, what tends to really suck as a motivational tool is all those things like brand reputation and long-term profitability and all that sort of stuff, which doesn't mean anything to a hydraulic engineer or an electronics technician or anything specific in terms of their performance appraisals. But if we look at the 10 reasons I went through today, we can actually see that, hey, if we do FMEAs, sure, it's going to affect our brand reputation in a good way later on because our thing is going to be reliable, but you're going to be on time. You're going to be on budget. It's not going to be your thing which embarrassingly fails when you do your first prototype testing. Your electric motor will be properly secured. That cable will be designed in a way that slamming the door won't destroy those solder joints. Your push to talk button is going to be really, really good to use. Customers are going to compliment your boss on how well that push to talk button was designed, and that's going to reflect well on you. These are all things which matter for you. Dawn, thank you very much. It wasn't a question, but I'll happily talk about it. So Neil has said, what's your take on linking process FMEA with design FMEAs? Okay, that's a really good question, Neil. The simplest way of linking design FMEAs with process FMEAs, and we didn't really go into the taxonomy of FMEAs today. Essentially, a design FMEA team can identify a root cause of failure, a potential root cause of failure, as something being, for example, outside of tolerances. What do I mean by that? So let's go to our smart lock example. A design FMEA team has realized that if our handle, which goes over a hexagonal shaft, if the socket of that handle is too small, such that it can fit over our hexagonal shaft, but it sort of has to stretch a little bit when it does it. That incorporates pre-tensile stresses, which is a bad thing for fatigue. So the design FMEA team will work out, hey, the socket of our handle needs to align with the dimensions of our shaft in a way that we don't have pre-tensile stresses. Now, that design FMEA team goes, I don't know what that clearance needs to be. They speak to the adhesive guys. They call up the adhesive guy on the phone and he says, you need to have a 0.025 millimeter clearance. between the shaft and the socket. And you say, okay, well, can it be 0.2? Can it be 0.3? What's the limits on your recommendation, the clearance? And he says, it needs to be between 0.2 and 0.3. Anything more above or below that will mean that you'll have problems later on. Brilliant. So you've gone through the thought process, you've identified what the clearance needs to be, and then you speak to the manufacturing team for the handle and work out what the tolerance needs to be for the handle. Same with the socket for the socket for the handle and the tolerance for the shaft. And you come up with specifications that need to that each individual manufacturing team needs to adhere to make sure the clearance is in that butter zone of 0.02 to 0.03 millimeters. Now, when you do that, the potential cause of failure will be one of those two things being outside of specifications. So you take that outcome of your design FMEA, and that goes into your process FMEA. How can your process fail? Well, the handle is going to be outside the specification. So the design FMEA comes up with all these specifications, and the process FMEA defines failure to be not adhering to that specification, and then off you go. So that's how they link, Neil. Did I answer your question well enough, or do I need to have another go? Just waiting for a potential response. Okay, thank you, Neil. Again, if I haven't done a good enough job, or you think of something later, please feel free to reach out to me as well. Paul asks, do you recommend hiring a facilitator or becoming a good one yourself? That's a good question, Paul, and there's no right or wrong answer. Organizations who take this very seriously I've seen have really good facilitation skills inside their team. That said, those are organizations which take it seriously. And when I say organization, I mean organizations, not just a couple of people here and there. It means that everyone from the boss down to the graduate student, graduate engineer, I should say, they, for whatever reason, the culture has been created over years to really value FMEAs, and that's where FMEA facilitation typically works organically. But for organizations which are not there yet or on the journey there, it's really hard, at least in my experience, for them to generate FMEA facilitators worth their salt. And sometimes it's difficult, even if you have a good culture, to have a good FMEA facilitator, because FMEA facilitation requires practice. So if your organization launches a new product every 2 years, and therefore you only do that sort of initial FMEA effort every 2 years, it's very hard to maintain that sort of those human skills that good FMEA facilitators have. So depending on your organization, if your organization is very mature when it comes to reliability, and if they do FMEAs a lot, then it makes sense to invest in creating your own FMEA facilitation capability. Identifying those couple of people who are going to be the champions of FMEAs, make sure they're motivated, make sure they like it, and they become your FMEA facilitator through training and through practice. Anything else, you might want to look at hiring an external facilitator. Does that answer your question, Paul? I can see a couple of comments coming as well. I'll get to you in a minute. No worries. Thank you, Paul. All right. Hojat, hopefully I pronounced your name correctly, asked, can we conduct a FMEA session on software only? So not exactly sure what that means, but I will have a go at answering it. COVID-19 has taught us that FMEAs can be done very well virtually. In fact, virtual FMEAs, I was speaking to my colleague Carl Carlson, the godfather of FMEAs. He's quite literally written the book on FMEAs. And I suppose we were both a little bit skeptical about how well you could do FMEAs virtually before COVID-19 came along, but COVID-19 came along and it forced us to do it FMEAs virtually. And it turns out, if you prepare enough and if you embrace technology, not only can virtual FMEAs be as good as in-person FMEAs, they can sometimes be better. There's pros and cons to each approach, and I personally really prefer, I really like having of human-to-human interaction. But in practice, we can't always do that. So virtual FMEAs, when done well, can almost have the same level of interaction, but it makes sure that if our resident expert is in Sweden, that person can easily dial into our FMEA, and therefore we are not burdened by problems associated with distances and travel. So if that was your question, hey Jack, can FMEAs be done on software only? We certainly are doing FMEAs virtually in terms of the medium the medium for making the FMEA happen. If, on the other hand, if you're asking, can we do FMEAs on software products only? The answer is yes. In fact, software FMEAs are their own beast because it's a very different system. A software system is very different to a mechanical system. So we have software-specific FMEAs. Hopefully that answered your question. If I haven't, please let me know while I answer some other questions. So I can see that David Kinsey, he's not asking a question, he's saying a very well-received comment. Great presentation, and this should be required viewing for all FMEA leaders and facilitators. Well, thanks for the feedback, and the idea is that if people can understand how valuable FMEAs are, then we want to do it, which means that we get good outcomes because people are bought in. Thank you, Long Chun as well. Volker writes, in most new plant designs, asset criticality is mostly decided post-build, which leaves or makes decision applications to apply to a FMEA aligned to criticality pre and during design, a major time consumer, thus ignored. How can this be changed? Well, that's a very big question, and it's challenging because, as you point out, criticality is often decided post-build. Now, there is some changes afoot. I know model-based systems engineering, for example, is looking to address issues like this, but it's not the answer. The reality is people need to want to do it, which means they need to understand why they need to do it up front. But again, there are some cultural and practical limitations for the challenge you're outlining here. In terms of, I think the simplest way of answering or trying to answer your question is that people don't do FMEAs because they think it's a time consumer. Now, no one does anything, or no one wants to do anything if the only thing they associate with that activity is the consumption of time. If we can somehow create a culture or a mindset where people see FMEAs as a generator of value, that's when things are going to change. So it's going to be through propaganda sessions like this one, where we say, hey, it's not just preventing failures 10 years from now, it's actually making sure our first design is a reliable design, so we're on time, on budget. Oh, and by the way, we can make our first design reliable and amazing as well. Wouldn't that be cool? And that's where people get invested, and that's where things start to happen. So I don't know if that answers your question well enough. But if it hasn't, please let me know and I'll resubmit. Paul says, I have experienced lots of resistance for software product FMEAs because software developers are unfamiliar with FMEA and don't generally fall under the same engineering structure as mechanical engineers. I'd actually say that's a common thread across lots of engineering disciplines, and it comes back to awareness and training. So there are software specific FMEAs out there, which by definition are software specific. So it's all about it comes down to the will of the organization, the culture of the organization, the leadership involved. And yes, software engineers aren't irrational, especially if they're being forced into design FMEAs which focus on the mechanics of stuff and being told to adapt to that process. Of course, they're going to feel burnt and jaded and not want to come back ever again. But if we can teach these guys and girls what a software FMEA is, how good it is, and how much value they will personally get from a FMEA, then that's where things will hopefully start to change. And especially in my FMEA training, I always start with the 10 reasons why you want to do FMEAs, because that gets the students motivated to remember all the stuff they're about to go through. Okay, thank you, Volker. Okay, so I'm going to move on to the comments section over here. Let's see. All right, some of them. So Hojat goes back to the whole software thing, I believe. So essentially, where I think Hojat's asking us to do a webinar one day about on what a software for me is and the techniques used, which I agree there's a need for, and I'll speak to Fred about including that in our schedule of FMEAs, a schedule of webinars moving forward. In fact, that's the last question. Okay, so we still have 24 long-suffering attendees. Are there any more questions, any more comments about the 10 reasons you want to do FMEAs? No worries, Hojat. It's we've got a list of things to do. In that will probably fall ahead of that software FMEA webinar, but and there are some software FMEA specialists out there, people who do nothing but software FMEAs, and maybe they could be a special guest webinar. What's we call a person who runs a webinar? It's not a webinee, webinar. I don't know. We could perhaps reach out to some of our colleagues moving forward. But more than happy to do one if we can get that in our priority list. Any more questions or comments? I think we're good, and I'll just maybe wait a couple more seconds, Fred, to allow for potentially long and detailed question to suddenly pop up. But I think we're closer to the end than the start. But for those of you who are still here, hey, thank you very much for turning up to the webinar today. We really do enjoy reaching out to you guys, and even though we don't hear your dulcet voices in response, the feedback and questions we get and the comments we get during these webinars make sure we know you're engaged and getting something out of what we do. So again, thank you very much for your support for this webinar. If there's any questions you have moving forward, please feel free to reach out. And of course, I do FMEA training as well. And there's tons of FMEA specialists. I really, if you want to learn more about FMEAs, then Ascendo's Carl Carlson has as much information as you'll ever need on how to do FMEA as well. Those amazing FMEAs. If you do want to take your FMEA journey and you just want to have a conversation or chat, again, feel free to reach out on my email address, which is associated with this webinar page on Ascendo. But beyond that, I'm guessing there's no more questions. You enjoy the rest of your Tuesday, wherever you are across the world, or whatever day of the week it is that you decide to rewatch or review this webinar. But again, thanks for turning up, and thanks for making this webinar an engaging experience, at least for me.